I am Professor Talat Ahmed, a professor of geology at the Department of Geology, Delhi University, and presently Vice Chancellor of Jamia Millia Islamia. Today we are discussing about the petrology of igneous rocks. The igneous rocks are those rocks that form on the surface or below the surface because of the partial melting that takes place in the crust or in the mantle. So, we will be discussing more based on the diagrams and mineralogies of different rock types. As we have discussed earlier, the igneous rocks are those rocks which are formed by partial melting of any rock, be it igneous or metamorphic or sedimentary, present in the source region, which could be crustal or which could be mantle or lithospheric. So, we have to understand how the mineralogy and petrology of the rocks are controlled because of different conditions of emplacement and extrusion. Igneous rocks are basically formed on the maximum amount of rocks that are formed are along the mid-ocean ridges where we have melting of the upper mantle and high degrees partial melting gives rise to basalts and high magnesian basalts, of which this is the major constituent of the ocean floor or ocean floor basalt. These rocks are also known as alkaline basalt when it comes from deeper sources. When the magma is generated at lower mantle, upper mantle boundary or slightly above that, as we know that the higher the pressure, the lower will be the degrees of partial melting. So, alkaline rocks which comes from deeper sources has to represent very low degrees partial melting. But because of depth, the pressure is very high, so their movement of the magma is much faster, and that keeps the pristine conditions and pristine character of these alkaline rocks. Now, when we talk about the lithosphere, which also includes both the part of the crust as well as part of the upper mantle, it is called lithosphere. Lithosphere is that part which is supposedly the oldest part in terms of the age of the source rock. So, these are also repository of lots of elements which are radiogenic. So, lithosphere has lots of radiogenic minerals and metals which will actually generate lots of heat, and then when it is added by the heat from the upper mantle or the movement of mantle plumes or adiabatic uprise, then there is melting in the lithosphere. So, lithosphere will give rise from the depth more alkaline rocks, and when it comes to the shallower levels, it will give rise to more basaltic and even granitic rocks. And similarly, there are different conditions when we talk about the mid-ocean ridge basalt. It is more of a extensive regime. Now, when these rocks are carried from the ocean ridges to the subduction zone, they will be subducted because they become cold and they are older, so they are subducted and then again heated up. Once they are heated up, and because they have been hydrous, because they have been interacting with the water which is present above the ocean floor, they are quite hydrous, so they melt partially much faster compared to a dry condition. So, when these rocks are taken to some depth in the subduction zone, they release fluids and also they release melt, which goes and also enrich the area which is sitting above the subduction zone, and that area, once they get these melts and fluids, their melting temperature also goes down, so they will also generate magma. So, you will have magma along the island arcs, where you receive magma from the subducting slab as well as from the slab which is above the subduction zone. So, you will have presence of bimodal volcanics. Okay. Mineralogically, they will be same, they will be basalt, they may be granite, they may be andesite, okay, but they are generated at different conditions, tectonic conditions. And to understand these, we have to study the trace elements to identify different tectonic regimes where they have been generated. When they are generated from the asthenosphere or upper mantle near the ocean ridges, they will be depleted in terms of the light rare earths and large ion lithophile elements. When they are generated at the subduction zone, they will be enriched because subduction zone will carry lots of fluids will come out, and these light rare earths and the large ion lithophile elements, they go into the melt phase and the generated rock is more enriched. So, they are all basalts or andesites, but different in terms of the trace elements, but similar in terms of the major elements. And mineralogically also, some of them will be having more of amphiboles representing presence of water, and some of them will be dry. So, as also we have discussed in our earlier lecture, that these rocks, igneous rocks, are generated at depth, and they can come to the surface as lava flows, or they can come and get deposited and melt and freezes at depth. So, when they are freezing at depth, they are known as plutonic rocks, and the ones which comes out on the surface, they are the volcanic rocks. So, now let us discuss one by one the major igneous rock types. As you can see that the whole earth, if you divide, the continental crust where we stay, mostly they are mostly intermediate to acidic, more of granite and granodiorite. Whereas, if you go to the ocean floor, the rocks are mostly basaltic. So, basically the ocean floor has rocks which are more heavier and denser because of the presence of iron and magnesium compared to the continental crust, where it is more of a sialic rocks, which is silica and alumina rich rocks. So, they will be having different mineralogies. We will be showing you some of the rock slides and how the mineral looks like, and then we will discuss about their occurrences and their important characters. So, what we see here is one of the most common igneous rocks of plutonic origin, that is the rocks which are crystallizing at depth. Granite is one of the most common, which is silica rich rock, and as you can see here that they have minerals which are mostly K-feldspar or orthoclase, and also you can see some of the biotite and muscovite and some of the amphiboles. So these are the common minerals that is available in the granitic rock. As I explained to you, the granitic rocks are derived from the crustal sources in different tectonic settings. So the most common being subduction zone environment or the island arc environment, where we have the granite pluton at depth, and on the surface we have the rhyolite. So this is the mineralogy as I explained to you, and you have lots of quartz in this, feldspars, K-feldspars, and mica, and then also amphiboles. So the next slide, the next very common igneous rock which is plutonic is known as gabbro. So gabbro is the equivalent of basalt, and they are mafic rocks based on the minerals, or based on geochemistry they are called basic rocks. So what we see here is they are mostly plagioclase and pyroxene rich rock. Since this is a plutonic rock, it has big crystals of plagioclases. Even in some cases you will see the tuning is very clear, but at places you will also have presence of quartz, which is not so common, but they are present in many cases. And gabbros are the rocks which are produced in very different tectonic environments. When it comes out at the ocean floor, they are equivalent to the N-type morb or normal morb. When they extrude as continental flood basalt, they are called continental flood basalt, and its equivalent at depth is the continental gabbro. And the third place where they are commonly seen is at the island arc or the subduction zone, where they occur sometimes as bimodal volcanics with acidic and basic rocks. So gabbro and granite on one hand, and basalt and rhyolite on the other hand. So which is very common rock assemblage seen in the subduction zone environment or arc environment. Now the other major rock types which is intermediate, so from more basic to more acidic, so this is in between intermediate rocks, where you have both plagioclase as well as feldspars, K-feldspars, and there are also presence of sphene, for example, and then there will be some pyroxene, some amphiboles. So it is a intermediate rocks. Its equivalent as a extrusive rock is andesite. So they are mostly restricted to island arcs and subduction zone environment. Now there is very interesting rock known as peridotite, where you can see that all these green ones are the olivine. So it is olivine rich rock with some pyroxenes and very rare plagioclase. So these are ultramafic rocks where you have sometimes 60 to 70% of olivine and pyroxene, and they represent very high temperature melt. When they intrude as a plutonics, they form peridotite. When it comes to the surface, they can be komatiite, they can be komatitic basalt, so very, very high magnesian rocks. So high magnesian is reflected by the presence of these big crystals of olivine, which you can see here very commonly. Many times we also see olivine as phenocryst in the olivine basalt, which we can show in some other slides. Now, thin section of basalt, as you can see here, that they are mostly plagioclase and some pyroxene. This is highly magnified, otherwise they are very, very fine grained rocks, but you can see that they still have very clear presence of plagioclase with twins. And as I told you that this will be equivalent to gabbros when they are plutonic. So these are dacite. So dacite is equivalent to granodiorite. So here you will have more plagioclase and then some pyroxene, some amphiboles, and they are composition wise, they are intermediate rocks. So, and this is the slide of andesite. As I told you that andesites are extrusive rocks which are very fine grained. You can see that the ground mass is very fine, almost glassy, with some phenocrysts of pyroxene and also some plagioclases. So these are rocks which are very, very common in subduction zone environment or the island arcs. So presence of andesite itself indicates that the tectonic scenario had something to do with the subduction of the ocean crust under the continental crust. So many times we will see also mixing of the material from the continental crust and their presence as phenocryst in the andesite. Okay, this is rhyolite. Rhyolite is the rock which is equivalent to granite, and this is very, very fine grained. As you can see that these are all mostly glassy with some of these as titanates and magnetite crystals, and they are having silica percentage more than 70%, mostly quartz and some K feldspar. So it depends actually. It can be very, very light in color and also very, very lightweight because it has very few mafic minerals, and because of that they are equivalent to the granite when it is crystallizing at depth and when it extrudes on the surface. Many times on the island arc tectonic scenario, rhyolites and basalt, they occur together with andesite. So the presence of rhyolite, andesite and basalt in any area indicates the presence of subduction zone in the past in this area. The best example is the Ladakh arc, which has all these components that has been discussed just now. All right, so we have seen how the igneous rocks are generated, how they evolve, and it is possible that mineralogically they may be similar from different tectonic settings, but when it comes to the trace elements and many times even the rare earths and major elements, there is a difference, and that is because of the presence or absence of water. So for example, when we discuss the presence of Deccan traps, which is present in India, in the western part of India, it is a typical continental arc rock, continental basalt, flood basalt. if you see the chemistry of these rocks, they are more enriched. Similarly, when you go into details of trace elements, what you see is that it has interacted with the lithosphere, because the magma which is generated from the mantle, it comes out, it interacts with the rocks of the crust and takes some of the signatures from the crust. Whereas same basaltic rocks, if you take from the ocean floor, it doesn't interact with any continental rock, because there is no continent available on the ocean. So the ocean rocks come out without any interaction with the material from the continent, will have a totally different chemistry. It is known as more depleted type basalt. So they are all basalts, whether it is ocean floor basalt or continental flood basalt or even island arc basalt, but they are all different in terms of their mineralogy, in terms of their trace element chemistry. To some extent, the major element chemistry, they are similar. Okay, because of that, they are called basalt. And even minerals, there will be some accessory minerals which indicates presence or absence of volatiles and water. So these are some of the information which will help us to understand, because when we go to field, we just see the rocks. We do not know whether, say for example, if we go a Precambrian terrain, we do not know that these rocks which were formed were part of an island arc, or that was part of a oceanic crust, or it was part of a simple flood basalt province. So these type of petrological studies is very important to decipher the tectonic scenario of the rocks that we study. So we have to look at the mineralogy, we have to look at the petrology, we have to look at the geochemistry to understand the genesis of a rock. So we can summarize that based on different diagrams that we discussed, that the igneous rocks are classified first as plutonic and volcanic. The plutonic rocks are those rocks that crystallizes at some depth, and it gives enough time for the magma to slowly crystallize and give rise to bigger crystals in the presence of volatiles. The same magma, when it comes to the surface of the earth, it comes out and extrudes as lava flow. The cooling is so fast that they don't get time to crystallize bigger crystals. Many times they will be just having glass and with some very, very minute crystals. So the mineralogy is not available for the more volcanic rocks compared to the plutonic rocks. So we have to use different techniques to describe these rocks based on the mineralogy, petrology and geochemistry of rocks to understand their genesis.